Sounds good to me.
Great. So this is a summary of the relative motion. When we talk about relative motion, what do we have in mind is that relative motion is a combination of two uniform motions, independent uniform motions. Okay, so now what is happening here is that one uniform motion is affected by another uniform motion, but those two are independent of each other. There are, let's say, three types of relative motion. So the first one, when we have a group of people or objects that are doing a uniform motion in one direction. So then we have a person A that is moving with a velocity A of, let's say, 5 meters per second going east. A person B that is moving with a velocity B of, let's say, 10 meters per second going east. A person C that is with a velocity C of 15 meters per second east. And what is happening here? We have an observer that is standing and observing this motion. So now you should be able to identify, this is type 1, you should be able to identify what does the observer sees. And what it is the observer sees whatever we described, because the velocity A, B, and C are in the relation to the observer, meaning that the observer is carrying that system of reference, which in our mind is northeast, southwest axis, but it is a system of reference. So then that's saying that the observer is standing, the velocity of the observer in the relation to the observer is equal to 0, because the observer is not moving in the relation to the northeast, southwest axis or the system of reference. The observer is carrying the system of reference within itself. And now we switch, and now we say, okay, let's see now what is the velocity of object A when is in reference to object A, meaning that, in reference to A, meaning that object A is carrying the system of reference. So what do we see? The velocity of object A in a reference to object A is equal to 0, while the velocity of object B in a reference to object A, meaning what does object A sees that object B is doing, will be 5 meters per second going east. You can say positive, it's the same thing. And then what is the velocity that object C is doing in reference to object A, meaning again that object A is carrying the system of reference, or what does object A sees that the velocity of object C is, then it is 10 meters per second going east. And when object A carrying the system of reference sees what the observer is doing, you will see that the observer is having a velocity of 5 meters per second going west. Is this clear? So now if we see and we observe what is happening in the reference to to B, then object A will have a velocity. Answer me on the chat, please. 5 meters per second going west. And velocity of object B in reference to object B, answer me on the chat while I'm asking this, is 0 meters per second. And the velocity of object C in reference to object B will be, what is it? 5 meters per second going, good. 5 meters per second going east. And the velocity of the observer in reference to object B will be 10 meters per second going west. Good. And now let's take a look and see what is happening in reference to object C. So what is the velocity of object A? In this case, will be 10 meters, great, 10 meters per second going west. And the velocity of object B in reference to object C will be, answer me on the chat, 5 meters per second going west, good. 5 meters per second going west. And the velocity of object C in reference to object C to itself is 0. Good. And the velocity of observer in reference to object C is 15 meters per second going west. Good. So this is the first type of question that you will see in the relative motion. The second type of question is that is known as the river question. And within the river question, we have river type question. Within the river question, we have different type of questions. So the very first one is when the swimmer or the boat are moving along with the current. So what do we have on this case? The questions that you will see on this case is that you have a river and you have an observer here and you have a current. The current can be east or west, doesn't really matter, it's the same thing. Let's say that the current is 10 meters per second going east. And then you have a swimmer or a boat that is moving with the current. So the velocity of the swimmer will be, or the boat is the same thing, will be 20 meters per second. And since it is going with the current, will be east. So on the questions, when you will see something like this, you will see that the swimmer is able to swim with a speed in still water of 20 meters per second. And then case A, it's moving with the current. So then you will do something like this. When we are referring to a relative motion question, what do you have to keep in mind is this, that the resultant velocity is the velocity of either the swimmer or the boat plus the velocity of the current. This is the relationship that we always refer to when we have a relative motion question. This is the relationship that we refer to. And now, graphically, on this case, what we will have is we will have a velocity of the swimmer that is 20 meters per second with the current meters per second east, plus the velocity of the current that is 10 meters per second. That is 10 meters per second going east. Therefore, the resultant velocity is a vector that starts at the end, the starting point, and end at the end point. Okay, this will be the resultant velocity graphically. Now let's see how we can do this mathematically. Since this is 1D situation, meaning that they are in the same line, they are collinear. They may be in the same direction or opposite direction, but they are on the same line. They are, and the word for it is collinear. Since they are 1D, then what we do is we add with positive or negative numbers. This is a shortcut for adding vectors in 1D situation. So then the resultant vector will be velocity of the swimmer going east will be positive 20 meters per second plus, so you always add because this is what you have here, plus the velocity of the current, since it's going east, will be positive as well, meters per second, giving a resultant velocity of positive 30 meters per second, or you can say 30 meters per second going east. If they're asking you now, what is the distance or what is the time? You can say the distance or the time. What is the distance that the swimmer will obtain? What is the distance or the displacement that the swimmer will obtain if he is swimming for 100 seconds? Then, being a uniform motion, you will say that the total displacement will be the resultant velocity times time. So this will be 30 meters per second going east times time, that is 100 seconds, and this will be 3,000 meters going east. Does this make sense? The second type of the second subtype, I should say, of the river type questions is when they are the swimmer and the current are against each other. So B is against the current. So you have a river that is still moving with a current of 10 meters per second. I will make a different number, not just 10. I will make now 5 meters per second going east. And since you are going against the current with a velocity of, let's say, 15, the velocity of the swimmer will be 15 meters per second, but now it is in the west direction. Why is it so? Because the problem is telling you that it is going against the current. Okay, as I said, the resultant velocity is always the velocity of the swimmer plus the velocity of the current or the boat. If there is a boat, then there is a boat. This is the main thing. This is where you have to start. This is where you have to start. So now we have graphically, it's something like this. We have the velocity of the swimmer as 15 meters per second going west. And then we have the velocity of the current that is 5 meters per second going east. So then the resultant velocity, which is a vector that starts at the starting point and end at the end point, will be something like this. Okay, we know that it's going west. Let's see now mathematically, how do we do this? This again is a 1D situation, which means that what we do is we add, why? Because we have the add sign here, with positive or negative numbers. So that means that the resultant velocity will be velocity of the swimmer going west. Is it positive or is it negative? Negative. Negative 15 meters per second plus, because the relationship dictates us. And now we have the velocity of the current going east. Is it positive or is it negative? Positive 5 meters per second. So then the resultant velocity will be negative 10 meters per second, or you can say 10 meters per second going west. Okay? And now if I'm asking you, what is the time that the swimmer will swim for, let's say, 500 meters against the current, and then what you will do is you will go d over VR, because this is a uniform motion. So 500 meters divided by 10 meters per second. And this is east-east, so east will cancel out. Then this will be 50 seconds against the river. Does this make sense? The third subtype of the river question is when the swimmer is swimming across, so across the river. So the situation will be, this is the river, and the current is still going east. So the current will be, let's say, 4 meters per second going east. But you as a swimmer will swim with a velocity of, let's say, 15 meters per second. And since you are going across the river, that means that you are going north. Okay, so now let's add more into this question. Let's say that the river has a width of 100 meters. And let's find the time that the swimmer will reach the other side of the river. However, in order to do so, we have to calculate the resultant velocity, or the velocity that observer sees as it is standing at the side of the river. So the resultant velocity will be, again, the velocity of the swimmer plus the velocity of the current. Now, we don't have 1D as we had in previous two cases, but we have 2D. But it is an easy 2D, because graphically, what we have is something like this. the velocity of the current is, sorry, the velocity of the swimmer is this way, plus the velocity of the current is this way. Therefore, the resultant velocity will be this one here. Okay. So now, since they are perpendicular to each other, we can find the resultant velocity, magnitude of it, as simply square root 4 square plus 15 square. So this will be 15.5 meters per second in magnitude, and as the direction, angle alpha will be inverse tangent of 4 over 15. So inverse tangent 4 over 15 is equal to about 15 degrees. You can say now that the resultant velocity is 15.5 meters per second at, we'll say 14.9, just to be more accurate, or 14.9 degrees east of north. This will be the resultant velocity. Does this make sense? Now, in this situation, what is happening is the swimmer is starting at a point here, point A, and it is heading to straight across at a point B. But actually, as an effect of the current, it is ending up at a point C. So that means, since we are dealing with a relative motion, a combination of two independent uniform motion, that means that the time that the object moves from A to B is the same as the time as the current is going from B to C in this direction, and is the same as the time as it is going from A to C. So this means time from A to B, same as time from B to C, same as time from A to C. But this means that since we have uniform motion, means that time will be displacement in this direction over velocity on this direction is the same as displacement on this direction over the velocity on this direction, BC, and displacement on AC is the same over the velocity on the same direction, AC. So when the question is asking you for how long the swimmer will reach the other side, so for how long the swimmer has to swim to reach the other side, you can pick any of those three ratios, as long as you know both of them. So as long as you know displacement on AB and velocity on AB, then you use that. So time that the swimmer will be swimming, it is the time that the swimmer will be swimming is the distance AB over the velocity on this direction. But what the velocity on this direction is the velocity of the swimmer. So now we have 100 meters divided by 15 meters per second, and this will be in your calculator, 15, is 6.67 seconds. And if I'm asking you how far downstream the swimmer will end up, then what do you have to calculate is the distance BC. How far downstream the swimmer will end up is the distance BC that I'm asking you for. For this, you can use the time that we know now, time times the velocity on this direction, BC, will be equals to the distance BC. So this will be 6.67 times the velocity of the current is 4. We said is 4. So times 4. This will be 26.67 or 7 meters downstream. You can check now by calculating the distance AC and dividing it by resultant velocity. You should have the same time. Does this make sense? So now the fourth type of question that we see, or subtype of question that we see at the river, is when we are adjusting to end up straight. So the situational diagram is something like this. You have a river, and then the current is, the velocity of the current is 8.0 meters per second going east. And what you are doing now is you want to end up straight. So this is what the resultant velocity should be. And I'm asking at what direction you should head to if you are able to swim in still water. So velocity of the swimmer in still water means that there is no motion of the water, is, let's suppose, 24 meters per second. So at what direction do you have to head to end up straight across the river? So graphically, or let's start with mathematically first. So the resultant velocity is the velocity of the swimmer plus the velocity of the current. On this relationship, being a vector relationship, what do we know in terms of the resultant velocity is we don't know what the magnitude is, but we do know what direction is. For the swimmer, we do know what the magnitude is, but we don't know what the direction is. Okay, and for the current, we do know both of them. So now, graphically, though, if we are looking for the velocity of the swimmer, then we can find that it is the resultant velocity minus the velocity of the current. Okay, let's see how this in vector representation will look like. So we have the velocity, the resultant velocity, which is straight up. Okay, it is something like this. If we were going with the velocity of the current, then we will go in the east direction. Since we have negative velocity of the current, we will go in the opposite direction. So what do we have is that this is where the swimmer should head in order to end up straight across. Now, in this vector representation of the adjusting, what we have is that the velocity of the current is given 8 meters per second. And the velocity of the swimmer in still water is 24 meters per second. Okay? So, and I'm asking you, what is this angle here? Alpha. How can you find this angle alpha when you know that you are dealing with, answers on the chat, with a right angle triangle? And what do you know is the opposite of this angle and the sine of this angle? Okay. So sine of angle alpha will be 8 over 24, which means that angle alpha itself will be inverse sine of 8 over 24. And in your calculator, inverse sine of 8 over 24 is 19.5 degrees. So this is what you have to do in order to figure out the direction in which the swimmer has to adjust to end up straight across. So now you can say that the swimmer will head at 24.0 meters per second at 19.5 degrees, and this is west of north. Okay, if we are asking here what is the resultant velocity, then what you can do is you can use a squared plus b squared is equal to c squared. So the magnitude of the resultant velocity will be the square root of 24 squared minus 8 squared. And this will be 24 squared minus 8 squared. The whole thing square root is equal to 22.6 meters per second. So this will be the resultant velocity, and it is straight north because this is what we are looking for, to end up straight north. And now if the river is 150 meters wide, then the time that it needs to reach the other side will be the distance 150 meters over the velocity on that direction. And the velocity on that direction for this case, when we are doing adjusting, is 22.6 meters per second. So 150 divided by 22.6 is equal to 6.64 seconds. And this will be the time that it needs the swimmer to swim to the other side of the river as it is adjusting the direction to end up straight across the point that it started. Does this make sense? The next type of question that we will see will be that is known as the wind question. Wind and plane question or wind question. So on the wind, what we have is simply adding two vectors. So using components. So if you have a velocity of the plane that is traveling with a velocity of, let's say, 150 kilometers per hour at, let's say, 34 degrees north of west, and the wind is affecting this motion at a magnitude of 50 kilometers per hour and the direction of 20 degrees south of east, let's say, then the relationship that we will use is the resultant velocity is velocity of the plane plus velocity of the wind. And since we are dealing with 2D situation, and it's not an easy one like in the previous case, but it is a 2D with horizontal and vertical component, then we will use the table of components, whatever we have done for adding two vectors. So what we have on the first case is between north and west, and it is a vector that goes like this with a 34-degree angle with the west axis. And on the second case, we have something between south and east, and the angle with the east axis. So this is 50, this is 910. The angle with the east axis is 20 degrees. So you will find the horizontal component and the vertical component of those vectors. Velocity of the plane, velocity of the wind, and resultant, and then you will do all the work as we have done on adding vectors, finding the horizontal component, vertical component, and then finding the magnitude and the direction. Is this clear?